Welcome to session 9 of Electrodynamics 2020. Today I wanted to start by just completing some discussion about Maxwell's equations. I want to just go through the formulation of Maxwell's equations in matter. Okay, so what we had is, in the case of the vacuum, we had the following equations. We had Gauss's law, div of E is equal to charge density divided by epsilon 0. We had that the divergence of B, as usual, was 0. We had that the curl of E, and I'll write the equations this way, plus the dB dt was equal to 0. And then we had that the curl of B minus mu 0 epsilon 0 dE dt, that was equal to mu 0 j. Okay, the reason why I write it this way, you remember, it's that all the derivatives, either via space or via time, are on the left-hand side, and the sources, the charge densities or the currents, are on the right-hand side. Okay, but in the books and in many other places, you'll find this term here written on the other side. It doesn't matter. As long as you adopt a convention and try to remember it, that's going to be good enough. So the discussion that we're going to have now is what happens in the presence of matter. Well, the first point to re-emphasize is that matter, so what? These are still correct. The only point we're making here is that if you do have matter, we've seen some simplified description of the pieces of matter that you might have in terms of their polarization and magnetization. Okay, so what we had, you remember, we had the electric polarization, which was a vector P, which was related to the so-called bound charges that we had through the relation that the density of bound charges was simply minus the divergence of the polarization. Okay? We also had the magnetization, you remember it was the density of like dipole moment per unit volume. So magnetization is also vector m, and this was related to the bound current density. Through the relation that the bound current density JB was the curl of M. Okay. So what happens in the presence of matter like this? Well, what's the one thing that we have to treat? We have to treat the time dependence of these equations, because you remember when we discussed electrostatics in the presence of matter, we already sorted out everything, but now we've got some additional terms in our Maxwell's equations that we want to rewrite. So, just a very simple discussion. Let's imagine that you've got a little piece of matter that I'll draw, if possible, a bit like a cylinder. Okay, so you've got that like this. And what I'm telling you is that this piece of matter has a certain polarization, vector P, going along the axis like this. So let's imagine this little surface here. What happens when we've got polarization? What does it mean, really? It means that there's a displacement relative to each other of the positive versus negative charges within this this little sector here. So if I just look at this little piece of matter here, what it really means is that there's a certain surface bound charge density induced on this side and compensated by this minus surface bound charge density on the other side here. And as the polarization changes in time, there's a current which goes, if you want, through this piece here, bringing the equivalent of the charge here through here. So, so when P changes, essentially what I can write is that there's a current which is induced. And the little current element that I have here, I would write, say, as a dI. What would that be? Well, it would be the change of this surface charge density, bound surface charge density at the edge here, with respect to time, okay, times the area that I would have here. So this area here is dA perp, okay, perp because it's perpendicular to the polarization that I have here, okay. So if you want, this would be just the derivative of the polarization with respect to time, okay, with the dA perp. So we can define the polarization current density okay, it's a density, I mean, it's known as the polarization current if you want, but you just have to remember that it's a polarization current, it's a current density, okay, Jp, as just this time change of the polarization vector with respect to time. Okay, so that's the amount of like differential current that you would have in this element here. Okay, there's one important thing that you have to understand here. It's got nothing to do with what we've seen before of the bound currents. Okay, these bound currents are really like little dipole moments floating about. Here, what we're talking about is really just the flow of positive versus negative charges in here. There's no circulation in here. Okay. So we can ask what happens with the continuity equation for these things. So what would happen is that, of course, my bound charges would have to be conserved. But if I look at the divergence of my polarization current, what do I get? Well, it's just using this definition that we have here. It's just the depolarization dt. And now, assuming that things are smooth in space and time, I can just invert the derivative. So it's just a derivative with respect to time of the divergence of the polarization. But of course, this is really by definition just minus the density of bound charges. So this just becomes minus d dt of rho bound. Okay, so indeed we have a kind of continuity equation for the bound charges, which just tells us that the following relation is obeyed. Okay, so if you want, the polarization current is the current associated to the conservation of bound charges. Now, it's just a little bit unfortunate to use these little indices here. It would have been nicer had JB been the current associated to rho bound, but you just have to remember this and not be too confused. It's kind of a historical accident. Many people use this convention here. But that's the expression of the conservation of charge locally for the bound charges that we have in our system. Okay, so what does that mean? It means that really we can think of the total charge density as being from two different parts. Okay, there are the free and the bound parts. So the total row is really just row free plus row bound. And this is really just the row free minus the divergence of the polarization. Okay, so for currents, we have a separation in 3 parts. Okay. Namely, we have free, we have bound, and we have the polarization. Okay, so really what I want to write is that the total current density that I have in my system, I will view as being composed of free currents. So these are the ones that essentially you control yourself in your lab setting. I will have the bound currents, which are the volume density of like dipoles, magnetic dipoles in your system, and I will have the polarization current, which just comes from the time dependence of your actual polarization. So again, I can use the identities that we've seen before to rewrite this. So there's the J free, and now there's the curl of M, okay, and there's the time change of the polarization. Right. So now we can just use these expressions here and plug them back into our Maxwell equations that we have here and just rewrite them in a more handy way for use in settings in which I've got matter involved in the calculations. So how does that work? Well, let's start with Gauss's law. Okay, so if I just rewrite Gauss, okay, I'm just going to use now that my total charge is composed of these two things. So I've got 1 over epsilon 0, and now I've got the free charge minus the divergence of P. So really what that means is that I can rewrite this as the following. I just have the divergence of D, which is equal to rho F. Okay, and you'll remember D is by definition epsilon. That's an epsilon too much. This is just epsilon 0 E plus P. Okay, for now nothing changed. This is what we already had in the static case. Okay, but now if we look at the Ampère-Maxwell law, so amp max, I will look at the curl of B, but now this is going to be mu 0 times a bunch of stuff. I've got my free currents, I've got my curl of the magnetization, and I've got the time dependence of my polarization. And then I've got the other term that we had before, mu 0 epsilon 0, dE dt. All right, so just by pattern recognition, you can see that what I get is that I can write this term here, I can bring to the other side here, and this one here I can just associate to what I had here, because once again I have the combination epsilon 0 electric field plus polarization, so this is going to be a time derivative of D. So I can rewrite this equation in the following form. Okay, where this field H, which unfortunately doesn't carry like a properly recognized name, people call it just the H field, many people call it just the magnetic field. So H is by definition 1 over mu 0 B minus M. Okay, so these are important equations that we have. So to summarize, Maxwell's equations in matter are the following. We have that the divergence of D is equal to the density of free charges. Okay. We have, let's see in which order I had written them here. So just like, okay, electric field on top, and then we have that the divergence of B is still equal to 0. That's not going to change. We have that the curl of E, okay, and again, if I just rewrite them with all derivatives on the left-hand side, dB dt is equal to 0. And now the curl of H minus the time derivative of D, this is now equal to the density of free charges. Okay, so these are just like handy rewritings for the case where we've got matter with polarizability and maybe also a magnetization vector included in them. Okay. So in many circumstances, we are going to talk about linear media. So in linear media, what we have is that the polarization becomes proportional via some electric susceptibility to the applied electric field. The magnetization would have some magnetic susceptibility with the applied H, and we would just write the vectors D as some epsilon times E, okay, where this epsilon here, you'll remember the nomenclature a little bit, this is a permittivity. And we would have the field H is equal to 1 over mu times B, okay, and this mu is so-called permeability. Okay, so once again, the value that these numbers take really change from material to material, and even from all circumstances to all circumstances, function of temperature, etc., etc. Okay, so we'll get back to that later. But in general, the relationship between these, like, if you want, original fields and those fields, they're called constitutive relations. They're in general much more complicated than these simple linear relationships here. Typically, you've got some tensor relationship here because the polarization doesn't have to go in the same direction as the applied field. But to keep it simple, we just do it this way at the moment. Okay. Now, maybe just to complete, it's important to talk about boundary conditions on these fields. Again, this is just a complete rehash of the story that we've seen before. Okay? So we can use Maxwell in integral form. Okay, for example, if I was to take the surface integral of D over a closed surface, what that would give me would be the total free enclosed charge. Okay. If I was to take the integral over a closed surface of B dot dA, that would simply give me 0. If I was to just take the integral of E dotted into dl, so here I'm just using Stokes' theorem, so this is now a closed circular path, this would just give me the time derivative of the flux. Like this. And if I was to take the same thing, once again, over a closed path of H dotted into dl, this would give me the total free enclosed current, okay, plus the time derivative of the integral over my surface of d dotted into dA. Okay? So we get, you remember the story using the Gaussian pillbox. And the Ampérian loop. Tricks, so I've got a surface like this, and on the one hand I want to do like a little Gaussian pillbox like this straddling the surface. So here's my surface, and then the pillbox kind of goes below like this, and I'm taking the height of this pillbox to be very, very small. So what that tells me, using this Gaussian pillbox, is that the perpendicular component of D has a discontinuity associated to the density of free charges onto this surface here. And similarly, the B field, of course, is continuous in its perpendicular component. Okay, so that's one thing. And then the other thing I want to do, I want to again consider the surface like this. And now what I'm going to imagine is that there's a surface current going like this. So this is a free current. I've got my my normal vector to the surface like this. And now I'm going to imagine taking a little loop. Well, it didn't like this particular one. Let me just erase this one. Let's do that again. So I had my wonderful surface, which I will redraw. And now I will do a little Ampérian loop like this, going under and then coming back up. I'll define a direction like this, which will be my little integration element dl, going like this. And now doing the usual trick. So if I consider, for example, integrating the electric field along this loop, then I would use this thing here. But then, because I'm taking the loop to be infinitely small, so this height becomes infinitesimal, then the right-hand side is just 0 because there is no flux. So that tells me immediately that the parallel component of the electrical field, so any direction parallel to the surface, 1 and 2 being above and under, if you want, this is just 0. And now if I take the last equation here, again, this term would vanish, but this one here would be the total free enclosed current. But because I have a surface current density here, I would pick up a contribution from this. And the contribution that I would get is really just the surface integral here, or the integral of this free surface current here. So what that tells me is that the discontinuity in the parallel component of H is, if you just work out the thing, you see you've got n dotted into dl, or I guess what I want to do is just n cross dl, which is a vector going this way. So this would be n hat, yeah, crosses into the dl, goes like this, and then this is parallel to kf. So essentially I want to have the component of kf along n cross dl, so I need to take some Kf dotted into n cross dl. But by a simple vector identity, you can just invert these operations here. So this is really just Kf cross n hat, yeah, dotted into dl. And that means I can now take the integral of this here. And now I just get the contribution coming from the surface current. So this is really just Kf crossed into n hat. Okay, so these are the boundary conditions that are obeyed by my fields. And again, so just maybe as an exercise for you. So specialize those to the case of linear media. And just see the equation and the equations in Griffiths. Let's see which equations these are. 764. Yeah, so that's the those are the ones that you want. Okay, so this is just the reformulation of our Maxwell equations for the case of matter. That's all I wanted to go through at this stage.